while they're setting up, I have some thanks to give. First of all, I want to thank the organizers and Enzo and Pierluigi and Enrico and Marco and Vincenzo and other people I'm sure I'm forgetting. But it's always an incredible pleasure to come to Urbino, not just because it's such a beautiful city, but because the intellectual environment is so stimulating and so fun. So thank you for having me back. It's always a pleasure. And also, I want to thank Enzo for that really extraordinarily generous and nice introduction of me. I have a lot to live up to, I think, but I will. So let's enjoy it. I actually want to. So I know that this is a mixed audience, and that there's in particular a very broad range of technical backgrounds. Some people know more of the technical details of general relativity and quantum field theory and cosmology than other people do. So I've tried to make the lecture, I tried to make much of the lecture non-technical, but there will be a few formula and equations thrown in there, and I will try to explain things as well as I can. But I very strongly encourage you to ask questions. If something isn't clear, if I'm not being clear, or something isn't clear on the slides, or you want to hear a little bit more about a claim I made, or you want me to explain an equation in more detail, please ask. I find students, I think, sometimes are reluctant to ask questions because they're worried that they may look, that they will look ignorant or something like that. But you can't learn if you don't ask questions. And I guarantee you, if you have a question, half the people in the room have the same question, and they're not asking it. So you will be doing everyone a favor if you ask the question. What else did I want to say? Right. The lecture today is not, there's not going to be much philosophy today. Today I'm really just going to be introducing the topic of cosmology, cosmological models, and explaining what dark energy is, why we think we need it, what the cosmological constant is. And I will touch on some philosophical issues along the way, but don't worry, we'll be making some deep dives into real philosophy starting tomorrow. Okay. So I'll begin with a quote from the great early 20th century British writer G.K. Chesterton. "Until we see the background of darkness, we cannot admire the light as a single and created thing." Until we understand dark energy, we cannot understand the universe insofar as we are able to at all. We cannot understand the rest of the contents of the universe and how they all fit together, how they affect each other's behavior, how they all contribute to the global structure of space-time, to the local dynamics of space-time. And that is so, and as I hope will become clear by the end of today, we really do not see the background of darkness right now. We really do not understand it. So as I mentioned, the lecture today will be, I'll explain what a cosmological model in general is. I will then go into some detail describing what is called the standard model of cosmology today, the so-called lambda CDM model, lambda cold dark matter concordance model. And I'll conclude by giving by canvassing, well, what it is we think that lambda, the cosmological constant, dark energy, what we think it is, and why it is that we really don't understand what it is, and what the most studied proposals are for its nature. So what is a cosmological model, which I will often abbreviate CM just for brevity, because to take up less room on the slides. So I'll begin by talking about the physical requirements and desiderata of a cosmological model. So first of all, it's important to always keep in mind that when we construct a model of the universe, well, when we construct a model of any physical system whatsoever, not just of the universe, it's always done at a particular scale. This may be a spatiotemporal scale, it may be an energetic scale, it may be QED amplitude, but there's always some scale at which the model is supposed to be appropriate and one hopes adequate. So in cosmology, the relevant scales are mostly distribution of galaxies, galaxy clusters, intergalactic nebula, globular clusters, and so on. And these span these different kinds of structures span an extraordinary range from 1 parsec to 100 megaparsecs and larger. So the very first thing you have to try to understand if someone says, "Here's my favorite cosmological model," I'm going to tell you about it. Get straight on what scale it is they're talking about. What is the granularity of the representation of the constituents of the universe that the model is supposed to capture? And for our purposes, we will be interested in models that are large enough so that, well, the models themselves aren't large enough. So the scale that the model is supposed to capture, if the model were that big, we would never be able to understand it. The scale that the model is supposed to capture is large enough so that the distribution of visible matter, so baryons, baryonic matter, photonic matter, leptonic matter, looks more or less homogeneous. And so that's roughly galactic clusters and larger, 100 megaparsecs. And when I say it looks more or less homogeneous, I mean at late times. So all bets are off for the very early universe. There's even more we don't understand about the very early universe than about relatively late times in the cosmos. To specify a cosmological model, you need to give me at least 3 things. You need to say what the space-time geometry is, and it's almost always, in today's physics, it's almost always going to be a 4-dimensional differential manifold. Well, the space-time geometry will be represented by a 4-dimensional differential manifold with a Lorentz metric with a reasonable topology. We'll talk about that in a little while. You have to tell me what the matter content is, not only what the types of matter are, but also what their equations of motion are, what the equations of state are, what the stress energy tensor is for the different kinds of matter. And you finally have to specify what the interaction is between the matter and the space-time geometry. And for our purposes, unless otherwise explicitly stated, we will be assuming that GR is a good theory, and we'll be working with GR. So the Einstein field equation, which I'm guessing many of you have at least seen, even if not fully digested, is GAB, the so-called Einstein tensor, which is a measure of the curvature of a space-time geometry, equals 8 pi TAB, the stress energy tensor of ordinary matter, plus lambda GAB, where lambda is the so-called cosmological constant, which is what we will be primarily focused on. Although, as you'll see, and as the G.K. Chesterton quote suggests, we really won't be able to understand lambda without having a grip on the stress energy of ordinary matter, and vice versa. And just to make clear some of the conventions I'm working with, I'm almost always going to use geometrized units in which I set C equal to h bar. Big G is Newton's gravitational constant. I set them all equal to 1 because they mostly don't matter for our purposes. I think there's one place in the lecture where I will need to explicitly include Newton's gravitational constant, and I'll flag that. But there's more. If you want to give me a cosmological model, what I've said so far doesn't yet suffice. Everything that I just described, these 3 ingredients, space-time geometry, matter content, interaction of geometry and matter, they have to be all appropriately related and are sufficiently articulated so as to determine the joint dynamical evolution of space-time geometry and matter, so as to support, depending on fixed scale, depending on what scale that we're working at, we have to be able to derive or construct representations in the model, at least of the cosmic microwave background radiation, the emission and absorption of radiation from discrete sources, structure formation from relatively small scales, say globular clusters, to relatively large scales, galactic superclusters. And we have to have some understanding of the redshift to luminosity relations. So I'll say a few things about each of those. So the cosmic microwave background radiation is it's a homogeneous, well, largely homogeneous, largely isotropic component of the Maxwell field, of the electromagnetic field that pervades all of space-time. It's black body radiation, so it has a perfectly, well, almost, actually really close to perfectly thermal spectrum. Today, the approximate temperature is around 2.7 degrees Kelvin, so really cold. And we think that it is in the very early universe, matter was so dense that light essentially couldn't travel very far, because it's continually being absorbed and re-emitted by the baryonic matter. But around 300,000 years after the Big Bang, when the density of matter became small enough and light was able to propagate more or less freely, then all of the existing free photons, the background electromagnetic field, kind of flew off and was free. And this is what we see. This is the cosmic microwave background. And it's because at that time, at that cosmological epoch, around 300,000 years after the Big Bang, because we think that the matter distribution, the baryonic matter distribution, was very homogeneous and isotropic. The photons themselves, the Maxwell field that was associated with it, itself is also homogeneous and isotropic. In fact, it's the homogeneity and isotropy of the CMB that gives us the strongest evidence of the homogeneity and isotropy of the matter at that early time in the universe. I'll say more about in a little bit about what the homogeneity and isotropy of matter exactly means. So why do we need emission and absorption of radiation from discrete sources? Well, because the universe is largely composed of discrete sources, stars, galaxies, quasars, and we need to be able to understand observing these sources is what gives us the most information about what's out there. So we need to be able to, in our model, to represent how it is that these discrete structures in the universe emit radiation, and also how they absorb radiation, because that's when we look at the sky and when we point our telescopes up and we measure electromagnetic radiation coming in, we have very good ideas about the characteristic frequencies at which various molecules vibrate, at the characteristic frequencies at which they emit electromagnetic radiation. But if a molecule emits a photon at a characteristic frequency, it will also absorb photons of the same characteristic frequency. So when we look at the sky and we see a spectral, we measure the spectrum of the electromagnetic radiation coming in, and we see a little dip where we expect, a little dip where there's fewer photons of a given frequency than in photons in the immediate frequency neighborhood. We think that the photons of that frequency are being absorbed by molecules, and that gives us some of the strongest possible evidence for what types of matter there are. We have to be able to understand structure formation because, yes, please.
What to say about 4.2? We don't need quantum mechanics at all, right? Or we don't need. Do we need to consider quantum mechanics?
So it entirely depends on what you're studying. So if you want to understand it, if you're looking at emission and absorption lines for galaxies, for nebula, for intergalactic dust, you don't need quantum mechanics. I mean, you need quantum mechanics to be able to calculate the spectral lines and the characteristic frequencies of absorption and emission, but you don't need it. You don't need it to model really to model the spectra. If you want to observe something like neutron stars, and potentially even white dwarfs, then you may need to employ quantum mechanics.
But we can take it as an external tool of the cosmological model, like.
Yes.
Okay.
Okay.
Mhm.
Because you got 2 hours. Let me ask you, why you use so complicated name for Friedman universe?
For FLR, you mean?
Friedman, Lemaitre, Robertson, Walker.
Mhm.
Why do you use so complicated name for Friedman universe?
No, just trying to give, trying to spread the credit around.
No, if you want to please everybody, you will never be able to do it anyway. But you know that Friedman wrote metric in 2225 for
Yeah.
closed
1922, 1923.
open universe. Sorry.
Mhm.
Okay, Lemaitre was later.
32.
No, before.
Mhm.
But 25, he by the way wrote this Sitter and expanded coordinate.
Mhm.
Robertson was 29 and Walker 1936.
Mhm.
Of course, when American write Robertson Walker universe, I understand this thing. It's called democracy. But why you use so complicated name?
Mhm.
Okay, when you could use just Friedman universe. Other people would not complain. I mean, nobody of them, of course, now can complain.
So historically, of course, you're right. Friedman was the first to develop the model in general relativity that we'll be discussing. But I think that the later people, Lemaitre, Robertson, and Walker, did make contributions to our understanding of those models.
No, because it's just metric of normal sphere, pseudosphere, and the simplest case was considered by Einstein and De Sitter in 1932. It was the flat universe. You see? Then if you want to be completely fair, then you have to add 2 other names. Okay, because we are in the conference of philosophy and history of science, I ask you natural question.
So I don't have a better answer, except that in large parts of the relativity community where I tend to operate, that's the standard name.
But do not care normally. They don't care about history. They do not check anything, as you understand. But these kind of things, actually, for instance, if you open called Turner book, there is called Robertson Walker method. And I had this kind of interesting discussion with Steve Weinberg, who was complaining why I do not refer to Robertson Walker. I think, but what for? Then he told he derived, they derived metric without using Einstein equations. Partially he was right, but on the hand, in a sense, you don't need the whole thing because you understand that metric is a symmetry. And this is the simplest possible symmetry which you are using. Symmetric of sphere, pseudosphere, or flat plane. Correct? You don't need killing vector, so you don't need anything.
So everything you just said is correct.
Yes.
But I don't want to get, I mean, do you really care so much about the nomenclature?
Historical justice, because Friedman was not there until Zeldovich started to fight. And until he started to write the things.
Okay. I think that we can go ahead with the lecture by thank you very much.
2 hours, is enough.
No, don't worry. I'll get you back when you're giving your lectures. So I invite everyone to call the space-time whatever they feel most comfortable calling it. Yes. Okay. So where was I? Right. That's right. So wait, I was like on 4.3 maybe, structure formation. Yes, right. So so a cosmological model has to explain structure formation because we look around and the universe is not in fact completely homogeneous and isotropic. It's on, our scales, it's incredibly lumpy and inhomogeneous. Luckily it's not, or else we would not be able to distinguish each other from each other. But on the scales we care about, even on the scales we care about, although it's an incredibly good approximation to treat the space-time as being homogeneous and isotropic, it's not. And it's still discrete. And we want to be able to understand how it is that these discrete structures developed and have the shape, the size, the mass, and the relationships among all of those that they do in fact have to each other. So the redshift to luminosity relations, we need to understand how it is that objects that are very far in the distant past that we're seeing with our telescopes, what the relationship is between the absolute luminosity, which is the luminosity, the amount of power that they're radiating where they are, and the luminosity that we see here. And that will not only be, of course, much weaker since we're very far away and the radiation is spreading out more or less spherically and becoming less and less dense, but also because radiation traveling through a gravitational potential will get redshifted. And one of the most powerful ways we have, in fact, of determining how far away things are is by the redshift. So we need to, but in order to understand what objects look like, where they are, we need to understand the relationship between the redshift we see them at and the luminosity we think they actually have at the source. And it perhaps goes without saying, but it actually must be said very emphatically that the cosmological model has to satisfy certain minimal observational constraints. At the least, it has to be compatible with the observations, even if not more strongly really predicting, characterizing, and explaining the observations. So, and for our purpose, what this means is that the cosmological model's core, the three elements I had listed on the previous slide, the space-time geometry, the matter, and the relationship between the space-time geometry and the matter, must have at late times an expanding Friedmann universe as in some relevant technical sense as a smooth limit. So if we're considering more fancy models where we take perturbations into account or we're allowing some anisotropies, it has to be the case that in some appropriate sense, as you coarse grain and remove the perturbations and remove the anisotropies, your space-time resolves into one of the really perfect, very highly symmetric, truly homogeneous and isotropic space-time models. And I guess I will just remark also that there are many interesting philosophical issues that come up when trying to think about how it is that we think we can know the large-scale global structure of space-time based on, let's face it, really relatively paltry observational data. And one of the most interesting, I think, debates in the foundations of physics over the last 50 years about this issue is what's called the observationally indistinguishable spacetimes. So it turns out that that general relativity is such a permissive theory in many senses that one can, in fact, you give me any general relativistic spacetime almost whatsoever, it can't be causally bizarre, but that's an incredibly, incredibly weak criterion. Spacetime is said to be causally bizarre if there's a spacetime point at which the entire spacetime is in the past of the point. So putting those spacetimes aside, which seem extremely unphysical, you can always construct another spacetime that is, in a precise sense, observationally indistinguishable from the first one. Every spacetime point in the one spacetime has a counterpart in the other, such that the two past light cones are isometric. So everything possible you could observe at the two spacetime points are identical. But the spacetimes have radically different global structures. They have radically different topologies. We're not going to consider those. We are really in the realm of standard, sane cosmology. So what are the epistemological and methodological requirements and desiderata of a cosmological model? Well, the first and most important is that it be easy to describe and to use. If you can't describe it, if you can't teach it to other people, if you can't use it, it's not much use for real science. And this may sound rather trivial, but I actually think it gets at something very deep about the epistemology of science itself. On my view of these matters, science is a very strongly communal affair. You know, the myth of the solitary genius figuring everything out is a myth. Scientific knowledge must be such as must be both expressible and expressed in a way that is communally assimilable and communally verifiable, or at least falsifiable, if nothing else. So it may sound somewhat trivial to say we require that the model be easy to describe and use, but it's one of the most fundamental aspects of scientific epistemology. And in our current epistemic state, because solutions to the Einstein, because we have really relatively meager knowledge about the entire solution space to the Einstein field equation, it is the case that, wait, did I say something funny? It necessarily follows that the cosmological model either is going to have some really powerful and strong spatiotemporal symmetries, which is what we'll primarily be considering in this talk, in these lectures, or some other kind of special property like conditions on the Weyl tensor that render the model mathematically, conceptually, and physically tractable. Now, I think it's worth spending a minute or two emphasizing this point. So the Einstein field equation, although it looks really elegant and simple, you know, just how much simpler could it be? GAB equals 8 pi TAB plus lambda GAB. Well, these symbols represent tensorial structures. So this is a tensor equation, and hidden underneath the hood of these tensors, if you write the Einstein field equation out in its most complete and articulated form in say some fixed coordinate system, they consist of 10 coupled nonlinear partial differential equations. And if you have any knowledge of differential equations at all, you'll know that by and large, solving one ordinary single variable differential equation, unless you're like dealing with something like the absolute simplest possible case, f equals f dot, exponential is the solution. They're unsolvable. Partial differential equations, even more difficult. Nonlinear partial differential equations, exponentially more difficult. Coupled nonlinear partial differential equations, tetration, more difficult. 10 of them, impossible. So the exact solutions we know of to the Einstein field equation occupy the most minimal, infinitesimally small part of the entire solution space, what we think of as the entire solution space, the Einstein field equation. So if you don't make rather radical simplifying and idealizing assumptions, you simply cannot make any progress whatsoever in this field. It seems to be an extremely fortunate state of affairs for us. We seem to be extremely lucky that the kinds of radical simplifications we need to make in constructing models, in constructing solutions to the Einstein field equation, actually turn out to be really, really good in the sense that they allow us to make extraordinarily accurate predictions. They allow us to understand the observations we're making to a very deep degree of accuracy and precision. So as far as I can see, the universe had no obligation to be so nice to us, but it is very nice to us. I can't resist. There's a wonderful poem by the 19th century American writer Stephen Crane. "Sir," said a man to the universe, "I exist." "That fact," replied the universe, "has instilled in me no sense of obligation." Well, the universe may have no obligation to us, but it has, in fact, been remarkably nice to us. So, wait, where am I? There I am. So the standard choices for the matter fields in a cosmological model these days are one or more of a fluid that pervades all of space-time with one hopes a physically well-motivated equation of state, a mixture of such fluids, each with its own characteristic forward velocity, particles with dynamics given by a kinetic theory, a scalar field, a Maxwell field, and in our case, a cosmological constant. And there is some, I would say, some debate or contention in different communities about how we should think of the cosmological constant, whether we should think of it as a kind of a space-time geometry term or as a matter term. My own preference, my own understanding is that it's more appropriately thought of as a matter term, and I'll discuss that in the third lecture. That's why I'm including it in this list of standard choices for matter fields. Okay, so we're going to spend a few minutes looking at a bunch of the physical quantities that cosmological models, as are standardly employed, possess. So again, we're moving into a slightly more technical part of the lecture. Please stop me, ask questions if you need to. So the physical quantities of interest that constitute a cosmological model is, first of all, the forward velocity of matter, whatever your choices of matter fields you have in your model. And of course, because the cosmological models represent structure at extremely large scales, we're generally assuming that the matter is more or less homogeneously distributed and continuously distributed. It's not going to be the case that you want to write down the forward velocity of every single individual galaxy or star or galactic cluster or globular cluster. What you rather do is you average. So when I say forward velocity of matter, don't think individual velocity of galaxy. Think the averaged forward velocity flow of all matter in a given spatial slice, the universe at a moment of time. The instantaneous spatial 3 metric. So recall that in general relativity, if you have a space-time and you have, time is going that way, and you have a space-like hypersurface, then if the normal is the space-like hypersurface, so let's say that this is the forward velocity of the matter on this space-like hypersurface, there is correlatively associated with that an instantaneous 3-dimensional Riemannian metric, positive definite metric, on the spatial slice. So the spatial slice really intrinsically, very small scales, looks like Euclidean space. It looks like three-dimensional Euclidean space. But of course, that's only at very, very small scales. The metric, the positive definite Riemannian metric over the whole spatial slice will generally have non-trivial curvature, will not be Euclidean. So you need to specify what that instantaneous spatial 3 metric is on every, all of space in a moment of time for the universe. You have to tell me what the rate of expansion of a characteristic 3 volume of matter is. So, if you look at a tiny little bit of matter on this space and you follow its evolution along the averaged forward velocity, generally speaking, a little volume of matter will either be expanding or it will be contracting. It's almost never going to be staying the same. And this quantity theta is the measure of the rate of that. I'm just calling it expansion because in fact, we think the universe we're living in is expanding, but it could be negative expansion, which would be, shrinking. There's the generalized Hubble parameter, which is just 1/3 of the rate of expansion, but it is really, really convenient to have this definition of the quantity, and that in turn determines the average length scale or scale factor. So which is more or less the normalized rate of expansion. Well, it's the norm. We have to know the rate of matter shear. So remember from continuum mechanics, from fluid mechanics, from solid state mechanics, that shear and stress are measures of the way that a continuum system is kind of, the internal forces tend to make it tend to want to make it internally. I'm having difficulty articulating myself today. I'm sorry. So if you think of a solid block of matter, let's say elastic, then the shear is, and you draw an imaginary plane through the system, then the stress are the normal components of the internal pressure, how little bits of the matter are pressing on each other and trying to move orthogonally to each other, and that's the shear stress. So you can think of the shear stress as how the matter is deforming as it moves and wants to contract and compress as it moves differently in different directions, generally speaking. The twist is just how much the matter is rotating. Yes.
Wondering if you can say something about footnote 4, because it's between the screen and I mean, I cannot read it.
So
is it just a semantic issue, or there is something?
No, I mean, well, it's partly just a semantic issue, but I think what I'm calling the Hubble parameter is very often called the Hubble constant, and I think that's misleading nomenclature, because the quantity is not in fact constant. It's not constant in time, and unless you're dealing with the very special case of a perfectly homogeneous space-time, it's not even constant over any of the natural space, any of the natural spatial slicings of the space-time. So it's called the Hubble constant for historical reasons. The term constant is used for historical reasons, but it's not. I just find that misleading and confusing. It's not a constant.
Can you explain what is shear?
I tried and I failed miserably. You want me to try again? So, okay. Actually, let me draw this. So let's say that, actually, I don't want to do that. So let's say that I have a cube of matter that has some elasticity to it. It resists deformation. It resists, if I try and press it and deform it, it resists that. If I try and like squeeze it or twist it or pull it apart, there's always resistance. And draw a tiny little imaginary surface inside the matter. So if the matter is under any kind of external force, generally speaking, if it's not in equilibrium, then there are going to be internally, different parts of the matter will be perhaps experiencing different forces. So there'll be pressure, there'll be forces on this point coming from the matter on each side of the plane, and these may not be equal. Perhaps something is pushing on it over here a little more strongly than it's pushing on it over there. So there'll be an inequality of the instantaneous force at that point, and the stress is the collection of all of those disparities in instantaneous force in the interior. The shear is the tangential component of the force. So how much if say I take this cube and I grab it over here and I try and slide it down and I grab it over here and I try and push it up, there'll be a tangential force, because it's trying to move up over here, it's trying to move down over there. And so the shear and the stress are the measure of how much inequality there is at each point in the internal configurational forces. And finally, there's the Weil tensor, which is the mathematical structure that represents the conformal structure of space-time, the distribution of the light cones, how the light cones in space-time expand and contract and twist and rotate and with respect to each other. In Minkowski space-time, the light cones are completely uniform, homogeneous. Every light cone looks the same. But in a generic general relativistic space-time with space-time curvature, light cones at different points have different geometrical structures. And the Weil tensor is that structure that encodes the distributional relative changes in the light cone structure. Mm-hmm.
We were talking about how universe is kind to us, and after that we started talking about these quantities and you go and
Oh, you're right. Thank you. I got distracted. Thank you very much.
Thank you. Sorry for mentioning.
No. Please do not apologize for that. That was great.
Thank you.
So, how did no one else catch me on that? No, I'm very grateful. So yeah, I guess I got carried away when I was talking about how nice the universe was, and I quoted Stephen Crane, and then I just blithely went on. So the other epistemological and methodological requirements in Desiderata are that the model has to support the construction or derivation of observational claims, and that is different than just constructing the kind of if you like, objective features of a physical system without reference to how it is when it's actually going to measure it, probe it, observe it, experiment on it. Because depending on the tools you use, you will need to take into account different features of the system, and you very often will have to take into account how the act of measuring and observing introduces certain kinds of systematic discrepancies, biases, distortions of what you're seeing. So a very common one in astronomy is so-called stellar aberration. You actually have to, our observational prowess is so good that when we're pointing a telescope at a distant object, we actually have to take into account the motion of the telescope as the Earth from the rotation of the Earth. We have to take into account the motion of the telescope due to the orbit of the Earth around the solar system, and various other features like that. So we have to have enough epistemic control over the model in order to model real observations and real experiments. And that is a highly non-trivial thing to do. We have to be able to incorporate so in order to do this, we have to be able to incorporate or otherwise understand the appropriate relations between the theories of that we use to construct the cosmological model and the theories that we use to model our measuring instruments, and also things like terrestrial weather, which affects the electromagnetic radiation that we're collecting with our telescopes. And finally, in a relevant and appropriate technical sense, our cosmological model should be stable under small perturbations. If I reach into the model and just tweak some small bit of the model very, very slightly, that shouldn't radically change other things in the model. Because if that were the case, given the fact that our observations have only a finite, rather limited degree of precision, we would never really be able to have confidence that our model was appropriate and adequate, because given, given observational error, given observational imprecisions, it could in fact be consistent with things being radically different, because very, very small changes in observation would be consistent with radically different, background theoretical structures. So we want our model to be stable. So the next physical quantity of fundamental interest to us in a cosmological model is the stress energy tensor. And the stress energy, in general relativity, quite generically speaking, the stress energy tensor is the only property of matter that couples with, that is both informs and is informed by the space-time curvature. That's what enters the Einstein field equation on the right-hand side. Just as in Newtonian mechanics, every kind of matter has inertial mass. The kind of generalization of that, as you move into relativity theory from Newtonian mechanics, is every kind of matter has stress energy. And in Newtonian mechanics, inertial mass was represented by a scalar, by a real number. But that gets generalized here, and this is intimately related to Einstein's insight that mass and energy are themselves intimately related. The stress energy tensor, the components of the stress energy tensor are the mass energy density, so the analog of the Newtonian mass, Newtonian inertial mass, and the spatial 3 momentum density, so the momentum of the matter on these natural space-like 3 slicings in our cosmological model. And because energy and mass are in a sense equivalent, momentum, which is in part characterized by the movement of mass, itself is relativistically equivalent to a kind of energy density. So the stress energy tensor also is, for the same reason, it encodes the isotropic pressure of the matter and the anisotropic stress, which I very painfully struggled to articulate a few minutes ago. So stress energy is mass energy plus momentum flux plus pressure plus stress. They all contribute energetically to determining the curvature of the space-time geometry. So the particular detailed physics of the matter is encoded generally in an equation of state that the matter will satisfy depending on the particular kind of matter it is, and on other imposed conditions, that relate the physical quantities to each other. So we will be almost entirely concerned with perfect fluids. A perfect fluid is a fluid for which the spatial 3, in the context of cosmology, for which the spatial 3 momentum and the stress vanish. And the idiosyncratic equation of state for this fluid, because just saying this doesn't tell you very much yet about how the fluid does behave. I've only told you how the fluid doesn't behave. So the equation of state, it tells you the pressure of the fluid as a function of, quite often it'll be the mass density and the local entropy density, but really it can be, the equation of state can be expressed as a combination of almost any thermodynamical variables. So the ones that you're probably all familiar with, for instance, is the ideal gas law. The pressure equals essentially is the temperature divided by the volume. That's the equation of state for an ideal gas. And you can have much more complicated relationships between the pressure and the mass density, the temperature, the volume, the shear, the entropy, whatever your favorite hydrodynamic or thermodynamic quantities are. You almost always impose some energy conditions that, for instance, we think quite reasonable, given our knowledge of matter in the universe, that locally we almost always measure energy to be positive. Putting certain kinds of quantum effects aside, we essentially never see locally negative energy density. But quite often, if all we do is fix the equation of state, that by itself won't guarantee that the energy density will always be positive. So you very often have to impose by hand this further condition to guarantee positivity of energy. We almost always require that the speed of sound in the fluid is again, in the units I'm using, where the speed of light is 1. So the speed of sound is bounded from below by 0. We don't want it to be able to travel more slowly than standing at rest. That really doesn't make much sense. And we also don't want it to be traveling faster than the speed of light. So this condition says that matter is locally stable and it doesn't violate causality. And then if one may also then go on to impose one further final condition. If the pressure vanishes, then you're dealing with dust, which doesn't interact, doesn't collide with each other, just particles freely moving. And that, by the way, is what we more or less think is the right way to model cold dark matter, which is a part of the standard cosmological model that we will not be discussing very much in these lectures. So probably for our purposes, the most important relationship among all of these quantities is the so-called Raychaudhuri equation. The Raychaudhuri equation says that the rate, so recall that theta was the characteristic expansion of locally of the matter, whether the matter is instantaneously moving apart or converging. This says that the rate of neighboring geodesics, freely flowing matter, the rate of how they converge or diverge, whether the matter is expanding or contracting, depends on the present value of the convergence or divergence, a function of the shear, a function of the twist, and the mass energy density. So the Raychaudhuri equation encodes the relative behavior of neighboring, if you like, particles of fluid. And this is sometimes called the basic equation of gravitational attraction, because one of the most characteristic, perhaps the most characteristic feature of gravity is that it causes nearby freely falling objects to accelerate towards each other if matter is positive and other conditions are more or less normal. And this tells you exactly how that works. We're almost done with relations among quantities, don't worry. So recall the definition of the generalized Hubble parameter. We use that to define the deceleration parameter. This is more or less equal to the spatial 3 momentum density. This tells you on a given space-like slice, how quickly is matter moving away from each other or moving towards each other. The mass energy density parameter, how much ordinary matter, baryonic matter, fermionic matter, photonic matter, what's the density of that? The pressure to density ratio, or barotropic index, this is for a perfect fluid, this is really almost always taken to be the equation of state. And finally, the cosmological constant parameter, which is lambda normalized by the Hubble expansion. Sometimes also called the dark energy density. So with all of these in hand, and applying the Raychaudhuri equation to these quantities, it's straightforward to derive that Q, the deceleration parameter, as a function of the other quantities, so we find that the rate of spatial expansion is fixed by the shear, the twist, and the stress energy density. Because recall, these encode the stress energy density of matter and the cosmological constant. So in the present day, observational constraints, in particular, the smallness of anisotropies in the cosmic background radiation, entails that the first 2 terms on the right-hand side are small. So this term and this term. What we know about matter, baryonic matter, cold dark matter, implies that the pressure of the matter is much, much less than its mass energy density. So this omega is small. So in the present day, it's a pretty good approximation to take the deceleration parameter to be 1/2 the density of ordinary matter minus the density of the cosmological constant. And you can already see, you can read directly off of this, that a positive lambda, a positive cosmological constant that was large enough would cause accelerated spatial expansion, because Q, the deceleration parameter, recall, is proportional to the second derivative of the scale factor. So there's the derivative of the scale factor is how quickly local spatial volumes are expanding or contracting. The second derivative is the rate of change of that. So if lambda is big enough, then Q is going to be negative, which means that space is going to be not just expanding, but expanding at an accelerated rate. So this is the characteristic property of a positive cosmological constant. So I've described in somewhat excruciating, possibly painful detail what a cosmological model in general is. We will now focus attention on what the standard model of cosmology, the so-called standard model of cosmology, is today, what most cosmologists, physicists agree as being more or less the best model for most purposes. That takes all the features of a generic cosmological model, fixes parameters, fixes relevant physical quantities of interest, fixes space-time geometry, and returns what we think of as the overall best model that we have. So the basic observations that the standard cosmological model is based on is that, at least locally, and remember, in cosmology, locally may mean 100 megaparsecs. There's spatial near perfect isotropy. So I realize I probably should have defined isotropy earlier in the talk. So a matter distribution, or any system, is isotropic if there's no privileged direction. No matter which direction I look in, things look exactly the same. So if things looked really different in that direction from everywhere else, that would be, in some sense, a privileged direction. I could use that to tell people what other directions to point to find things. But in a perfectly isotropic world, I can't do that. There are no markers that allow me to pick out a direction in space. And the observation of near perfect isotropy comes from the cosmic microwave background. It is, so far as we can tell, isotropic to a very, very high degree, about 1 part in 10 to the 5. We assume that the matter content of the universe is very well modeled by a perfect fluid. In fact, by a very simple perfect fluid. So then, as we already remarked, we know that the acceleration of matter, the shear, and the twist are all going to be 0. And this will be true if and only if the Weyl tensor is 0, as it turns out in this kind of model. So the left-hand side captures the idea of local spatial isotropy, because if there's no acceleration, if there's no shear, if there's no twist, then every direction looks exactly the same. If there were twist, then the axis of rotation would define a privileged direction. If there were shear, then then I could use planes of maximal or minimal shear to define privileged directions. But if there's no shear, there's no twist, there's no acceleration, there's no privileged direction. The right-hand side says that space-time is conformally flat, that the light cones are, in a very important sense, more or less uniform. Things locally look a lot like Minkowski space-time if all we're looking at is the way that the light cones nearby each other behave with respect to each other. It turns out that isotropy is an incredibly strong assumption. Well, incredibly strong property, I should rather say. It's not an assumption. It's an incredibly strong property. Because if things look exactly the same everywhere I look, in every direction, then at least locally, I know that things, in fact, look more or less the same no matter how I move. If things look exactly the same here, then if I move 5 feet to the right, 3 meters to the right, things should look exactly the same in all directions as before. But that means that the state of matter, the state of the universe here, is the same as the local state of the universe here. So the matter distribution, the space-time geometry is spatially homogeneous. That follows from isotropy. There are no homogeneity means there are no privileged places. Aristotle, infamously thought that there was a privileged spatial place, the center of the earth. But we don't think that. At least those of us who are sane and reasonable don't think that. So this means that the local state of the fluid is the same everywhere on the natural space-like slices of the cosmological model. And mathematically, that's expressed by saying that if you know any fluid mechanics, the so-called convective or material derivative vanishes. The space-like convective or material derivative vanishes. So this is just a nice diagram capturing the idea of illustrating the idea of isotropy. It says that if these lines represent the average fluid flow, the average pore velocity of the cosmological fluid, then there's spatial directions S1 and S2 are completely equivalent, both geometrically and materially. If I rotate from S1 to S2, things look exactly the same. This is an illustration of spatial homogeneity. There are no privileged points. P and Q are on every spatial slice everywhere, look exactly the same, are locally in the same physical state. If I take the spatial slice and slide the entire matter distribution, so-called Leibniz shift, 3 meters to the left, everything looks exactly the same. There are no privileged places. Let's make one further assumption, the so-called Copernican principle. We are not privileged observers. We don't occupy a physically, and so not an observationally, special place in the universe. Why do we assume that? I really don't know. It works really well, and people give all kinds of philosophical arguments in defense of the Copernican principle. I don't find any of them really very compelling. I think the best defense for assuming it is it works incredibly well. And again, as far as we can see, the universe really does look more or less the same in all directions, no matter how far we can see. That seems to give some empirical support for the Copernican principle. But we almost certainly can't see the entire universe. There's large expanses of the universe, most likely, that we have no causal contact with whatsoever, but that may, in fact, eventually appear to us as our cosmological horizon spreads out. And the Copernican principle basically says there are no surprises waiting for us. What can justify that? Nothing, really. But except the fact that so far it's worked really well, and we're going to keep on using it and hope that it works really well. Mm-hmm.
Yeah, so I just wonder, it doesn't follow then from a dynamical principle or anything like that, like a Galilean.
I mean, you can. I have no doubt if you're clever enough, you can sit down and come up with one that will imply it. But unless you have some good justification for that dynamical principle, then.
But Erik,
Mhm.
can I ask you a question? Why do you think? Can you give one argument why we have to be in the special place?
I can't. No.
We are not in Vatican, right?
Mhm.
Therefore, okay, I don't see any point why we have to be in the special place.
So I can give you no argument for why we are in a special place, but I also can't give you an argument for why we're not in a special place.
No, give me one particular argument why we are in the special, why we could be in the special place.
You can't give an argument for that, but you also can't give an argument that we're not in a special place. So I think I mean, do you think that there is a justification for the Copernican principle over and above? It works really well.
Of course, because we are nobodies,
Mhm.
and there could be the same nobodies everywhere.
I agree that we effectively are cosmological nobodies. I think that sounds very plausible, but plausibility is only that, plausibility. It's not a definitive argument.
But what do you mean on the definitive argument? This is the question again, because if, for instance, I would imagine that I am solipsist and all of you are my imagination, you cannot rule out this kind of hypothesis.
You can't, but actually, I think Bertrand Russell had a really wonderful remark about that. He said, if I were really a solipsist, I don't know why I would spend so much time writing these kind of crappy papers and books that I do, when with complete virtuosic effortlessness, I could write a much better book by opening a volume of Plato or Einstein. So I think that there's some reason that one can give some kind of reason why why solipsism may not be the best idea. But for the Copernican, and I think in a similar way, one can give plausibility arguments for why the Copernican principle seems like a very compelling and natural thing to assume. But I think that's the best we can do, is to give prima facie compelling, intuitively plausible justifications for it. I don't think we can derive it from some deeper physical principle that has any empirical entrenchment. That's what I would take to be a definitive argument in favor of it. So the Copernican principle, no. Yeah, absolutely.
So like, I agree that it doesn't look like a very plausible principle.
No, I think it is
But
plausible.
maybe not like compelling, maybe. It's plausible, but not compelling. But the negation of that principle would seem to me to be even more implausible than the principle itself.
Well,
But I'm curious about your
I think that's
opinion
what
on the kind
Slava
of
was
like,
suggesting.
whether there's like a symmetry between this principle and its negation.
I mean,
If you see what I'm getting at.
yeah, I do.
Yeah.
And I think that's exactly what Slava was pushing me on. I would say, insofar as I have no derivation of the Copernican principle from some deeper underlying, physical argument, that's based on empirically well-entrenched physical principles. But I also don't have such an argument for the negation of the Copernican principle. In that sense, they do seem to me to have a symmetry, the kind of symmetry you're talking about. Insofar as there are, I think, kind of intuitively plausible reasons for that, various both, I think, psychological, sociological, and philosophical and physical reasons for that favor the Copernican principle, it seems reasonable to assume it. And then the fact that it ends up working incredibly well is, to my mind, finally the best justification we can give for it. I know, but things have radically changed. Well, at least among scientists.
No. Greeks were assuming already this, I think, Aristarchus, yeah? Copernicus principle. He was putting the sun in the center of our planetary system. But you know why actually this theory was abandoned?
Well, Eric, it was abandoned because it wasn't abandoned. Just no one else believed. No one else believed it except Aristarchus.
It was abandoned on the basis of observation. This was why there was introduced this Ptolemaic system with epicycles. And when Copernicus came, he was heavily criticized by Tycho Brahe that it's not in correspondence with observation.
Right, because there was no parallax.
Yeah, no, because actually everybody was assuming that planets should move on the circles because it's most perfect. Curves, you see, and the things became okay only with Kepler discovered. So three laws, you see. But
So-
Copernicus had no reason to make this assumption.
I think that's right as a historical remark, but yeah, the evolution of the idea of the Copernican principle is what we call the Copernican principle is fascinating, but it's not, it's still, that still sheds very little light for me on why we really seem to believe it so fervently today.
Today it's established.
Mhm.
By observation.
Yes. So the Copernican principle implies, in a rather weak sense of the word, this is a what I call a physics implication, not a logical or mathematical implication. The cosmological principle, which is that the universe is everywhere spatially isotropic and homogeneous. It's locally spatially isotropic and homogeneous. We get that from observations. The Copernican principle, physics implies that the universe is everywhere spatially isotropic and homogeneous. Now let's place some constraints on the topology of the space-time. We're going to assume that the manifold has topology, the real line cross some the Cartesian product of some three-dimensional connected topological manifold that consists of one or more of some Cartesian product or connected topological sum of the real line, the circle, the two-sphere, or the three-sphere. Except it turns out one combination is not allowed. S2 cross S is for various mathematical and observational reasons not allowed. Now, and this may seem, in many ways, this is a very natural assumption to make. But it's not imposed on us by observation, and it's not imposed on us by mathematics, and it's not imposed on us by any physics that I know of. All the observations we have are consistent with space, the three-dimensional manifold that represents all of space at a given moment of time, can actually have, at least mathematically, and I think possibly physically, much more exotic topologies. But because they're not easy to work with, they're not easy to conceptualize, they're not easy to use to make predictions, cosmologists tend not to, just tend to exclude them almost by fiat. I'll discuss that a little bit more later in the lecture. And we now have F spacetimes, or FL spacetimes, or RW spacetimes, or FLRW spacetimes. And the general FLRW metric, I'm gonna keep on saying that because I enjoy irritating Slava. So the general FLRW metric in natural coordinates is this is the time component. This says, you know, that this is the one-dimensional real line of time. This is the metric on the three-dimensional space-like surfaces, all of space at a given moment of time. And so this part of the metric says that space is, if this F is signed, then space is spherical. If this F is just R, that means space is flat. It's Euclidean geometry, basically. And if this F is sinh, then it's a hyperbolic geometry. And A is the scale factor. So A as a function of time, if A is getting bigger, then the three-dimensional space is expanding. If A is getting smaller, the three-dimensional space is shrinking. If A is a constant, then three-dimensional space is just hanging out and not doing very much. So it turns out that the metric places the FLRW metric places pretty strict constraints on the topology of space. If the universe is open, which means that sigma, the three-dimensional manifold, the metric on it is either flat or hyperbolic, which hyperbolic means negatively curved, then the intrinsic, then sigma is non-compact as a topological space. So it's going to be, it's almost always taken to be I shouldn't be R4, that should be R3. So it's almost always taken to be R3. Again, we're assuming topological simplicity. if it's a closed universe, that means that that all of space at a given moment of time has an intrinsic has a spherical intrinsic geometry, the intrinsic geometry of a sphere. Then sigma is going to be compact as a topological space. And remember, when I say it's compact or non-compact, I don't mean as a submanifold of the space-time. I mean, if you consider it as a topological space in its own right. And so again, the most common choices, if we're dealing with a closed universe, is the 2-sphere cross the real line, or the 3-sphere, or the 3-torus. But it's almost always actually the 3-sphere. But again, a caveat is that although there are very compelling both mathematical and physical reasons to think that the intrinsic geometry of the 3-dimensional space-like slices really constrains the topology of the 3 slices, it's not strictly speaking correct as a mathematical claim. Because one can in fact have flat or hyperbolic geometries on compact 3 manifolds. The simplest way of doing it is just to put a flat metric on R3 and then make topological identifications. Just say I'm going to, after some finite time, I'm just going to identify points. So I turn R3 into a big cylinder, or into a truncated cylinder, or a torus. Or we can take quotients by nice subgroups of the isometries of the Euclidean geometry, and that will give us a compact 3 manifold on which there is still a flat geometry. But cosmologists tend not to do that. The sentiment is that this is not natural, and you'll find this word being employed over and over again in cosmology, not a lot of physics, but I think especially in cosmology. To me, philosophy is very, very clearly entering the door here, because natural is not a well-defined notion to my mind. It's the idea that certain kinds of topologies associated with certain kinds of geometries are natural or not natural is rather far-fetched. There's a wonderful quote by Rousseau from the Second Discourse. When the word natural enters the room by the door, philosophy jumps out the window. And I think the idea of some things being natural invoked in an argumentative context to rule something out or to spoken up in favor of it usually means you don't really have a good argument for the claim, but you have a very strong sense it must be right. And so then you use the word natural. And I think that is possibly what is going on in a lot of the claims cosmologists make, that, for instance, having a flat or hyperbolic geometry on a compact manifold is not natural. Yes.
Not understand exactly what, according to what, is not natural.
So, what is not natural is having an open universe, a flat or hyperbolic intrinsic geometry.
Okay.
But having the topology of the spatial slices being compact. So, being a torus.
One of the 3 possibilities is not natural for the world.
Yes.
Okay. 1984.
Yes.
Okay.
He says that explicitly, that this possibility is not natural, and he just leaves it at that and moves on. So for our purposes, the most important properties of FLRW spacetimes is that they're globally hyperbolic, which more or less means that the initial value problem is well posed. If I give you all of space, if I tell you what the matter distribution is on all of space at a given moment of time, and I tell you what the extrinsic geometry is, how the space-like slice kind of fits into the larger space-time manifold, then I can use the Einstein field equations to evolve that data forwards. I can solve the initial value problem. Now, this isn't strictly speaking true, because in fact, the initial value problem in the mathematical sense of Hadamard as being more or less stable under small perturbations That's what we tend to mean when we say that initial value problem is well posed. Actually, for a lot of different kinds of perfect fluids, the initial value problem, including dust, the initial value problem is not well posed. But we tend to ignore that, and we can actually make a lot. We actually can make a lot of progress and do very well ignoring that. So we're just going to follow common practice and say that in fact in FLRW under using the standard models for fluids, the initial value problem is well posed. It turns out that this relation, recall that I wrote down as an approximation before in generic cosmological models, is now exact. The deceleration parameter, the 3 momentum of matter, is 1/2 of the ordinary matter density minus the cosmological constant energy density. And it's now easy to see that the space-time cannot be static. It can't be unchanging in time if there is non-trivial matter or if there's a lambda. Because if Q is not 0, then space is expanding or contracting. Matter is moving apart or moving towards each other. So things are changing in time. So it's only under incredibly special conditions that you get an FLRW space-time that is static, that doesn't change over time. That also means, because it's not static, because there is no time-like killing field, we don't have strict energy conservation. We mostly can get away with ignoring it and treat energy as being conserved. It's an incredibly good approximation for almost all purposes in cosmology. But strictly speaking, energy is not conserved. This is a very puzzling feature about general relativity, that in a generic relativistic spacetime, there is no energy conservation. Some people like to claim that this is related to the fact that gravitational energy is not locally well-defined, but I don't think I don't personally find that a very helpful way to think about the fact. It's just that general relativity is quite different from classical Newtonian mechanics. You have energy conservation in classical Newtonian mechanics for various reasons, both physical and mathematical. You lose it in general relativity. And in our best cosmological model, we don't have it, at least not strictly. So there are cosmological particle horizons. I'll show you a picture of what that means in a minute, so I'm not going to try and describe it. And except under extremely special conditions, much like the fact that the space-time model is generally not static, the FLRW space-time will have an initial or final singularity. Either a big bang, a big zip, a big crunch, or a big rip. And I'll show you some pictures and tell you what those mean in a moment. They can also have so-called sudden singularities, which are really, really odd. And a sudden singularity is it's an event in the interior of space-time. It's not an initial singularity like the Big Bang or a final singularity like the Big Crunch. In the interior of space-time, physically important quantities like derivatives of the scale factor, pressure, can diverge. They can become quote unquote infinitely large in the middle of space-time. And yet that in such a way as not to hinder the dynamical evolution of the geometry and of the rest of the matter. So these are incredibly weird and really difficult to understand. And I don't think we still have a very good grip on exactly what they may mean or whether anything like them actually occurs in the real world. But it is at least it is permitted as a feature of the standard model. So I promised you some pictures. So these are so-called Penrose or conformal diagrams of various kinds of FLRW geometries. So in a Big Bang, so in all of these diagrams, time moves from the bottom to the top. So the Big Bang starts out in incredibly dense, tiny, infinitesimally small region and expands outward explosively. And in this, these are conformal diagrams for the flat FLRW models. So all of space at a given moment of time is Euclidean, no curvature. And the reason why, if you're not familiar with Penrose or conformal diagrams, it may be confusing to you that I said the Big Bang started out from an infinitesimally small state, and yet it's the longest line in the diagram. It's because conformal diagrams are diagrams that give very, very perspicuous representations of the causal structure of the space-time, of the conformal structure of the space-time. But they do so at the cost of distorting other features of the space-time, in particular volume. So don't think about these as being accurate representations of space-time volumes. It's only the causal structure. So this is an initial singularity. This is so-called future null infinity. So this is a light ray starting here and traveling out. That's actually an infinite distance. But of course, you can't represent that very well on a diagram and on a finite whiteboard. So the other thing that conformal diagrams do is they bring infinity in to a finite distance for representational purposes. So this is actually future null infinity, the endpoint of all null geodesics of all light rays. This is future time-like infinity. This is probably the simplest model. This says it starts with the Big Bang and just keeps on expanding and expanding and expanding forever. So even though it looks like the volume is shrinking, actually the volume is expanding. The volume's getting bigger and bigger as you go forward in time. Just the diagram distorts that in order to capture the causal structure. So this is a big rip singularity. In this case, the kind of a naive volume geometry of the diagram is more or less suggestively accurate, because the reason this is called a big rip singularity is that space is expanding very, very quickly, in fact, at an ever accelerating rate. Matter is flying apart at ever faster rates. And finally, the expansion rate becomes so extreme that space-time rips itself apart. The space-time geometry no longer is well defined. And that happens after a finite amount of time. That's also, I think, at least for me, very, very hard to visualize, very hard to understand. I mean, I can give you descriptions of how geodesics behave. I can give you, mathematical descriptions of how the density of matter behaves. But the idea of space-time ripping itself apart so that not even, fundamental particles like leptons or quarks can maintain their structural integrity, it's a rather difficult physical concept. It's a rather difficult concept to really digest. But again, it is a possibility in these models. So these are diagrams of positive curvature, FLRW spacetimes. And here we have the possibility now not only of a Big Bang, but of a big crunch. And that's when, so the Big Bang the universe starts out kind of infinitesimally small. It begins to explosively expand, but under the weight of its own self-gravitation, the expansion isn't fast enough or violent enough to keep on going. Eventually, all the matter is mutually gravitating. It's trying to pull all the matter itself, back together, and eventually it succeeds. The expansion of the matter slows down, stops, and matter begins to recontract. The universe begins to recontract until the kind of time reverse of the Big Bang happens. All of the matter and the universe collapses back to an infinitesimal point. The universe shrinks and vanishes.
You mean the body or the point?
Everything. The entire universe is. It's not just that matter is shrinking and condensing. The entire universe, space is getting smaller and smaller and smaller. Just as right now we think space is getting bigger in a certain, in a sense, the universe is expanding. When you hit this inflection point in one of these models, space itself begins to contract. And
Perhaps it's better to see not a lot of time because we have question
Mhm.
for 30 we should make a stop for the
Okay, so then I'll go on for a few more minutes and then stop for questions. Okay. So in that case, so very quickly, a cosmological or particle horizon. So this is a representation of de Sitter space, which is a particularly simple FLRW model, and we think that in many ways is a very good representation of a lot of features of the world. But for our purposes, if this is past infinity, so this is, if you like, going infinitely far back into the cosmological past. This is an observer traveling as far to the future as they possibly can. This is the past light cone of the observer's world line. And you can see that in this space-time, there's only so much of the past of the space-time this observer can ever see. So an observer over here, and an observer over here, their past light cones, their causal paths need not intersect. There may be no common causal path whatsoever. And that's what the particle horizon is. So this is how much of the universe this observer can ever, in principle, see, no matter how far to the future that observer travels. And that, we think, actually does represent a large part of the causal structure of our space-time, that we only ever see part of the causal past of the universe. So I'll skip this in the interest of time. The basic take-home message of this slice is that FLRW works unbelievably well, works really incredibly well at modeling a lot of the observational features of the universe. And then I was going to go into the early to mid-90s pre-supernova measurement situation, what people thought about the structure of the universe there. But you know what? I think this actually may be a pretty good. No, actually, two more slides and then I'll stop. That would be a good place to stop, and I'll pick up tomorrow. So in the early to mid-90s, the situation in cosmology was that observations strongly favored a near flat FLRW with lambda essentially equal to 0. No cosmological constant, no dark energy. And the observations that strongly favored this were an expansion from a hot Big Bang. We see the universe expanding. We see, and this expansion explained the galactic redshifts that we see. The fact that the farther away a galaxy is, the more redshifted the light is that reaches us. The homogeneity, both the fact that there is a cosmic microwave background and its homogeneity and isotropy. The large-scale structure formation we see, the kind of qualitative features of the distribution of galaxies and clusters of galaxies, and actually, remarkably enough, the standard cosmological model not only gives us all of this, but it actually allows us, and this is one place where quantum mechanics is in fact involved, essentially, that it allows us to calculate the relative abundance of light elements in the universe, how much hydrogen there is compared to how much helium there is. And the model allows us to calculate that, to make predictions of that to really extraordinary accuracy. That is very, very powerful evidence, I think, in favor of this model. The fact that invoking the quantum mechanics of nucleosynthesis allows us to predict the relative abundance of hydrogen and helium. It almost gets lithium, but not quite. But I mean, it's good. It's good enough so that there's reason to think that if we had better understanding of the nucleosynthetic processes, we probably could get lithium right. But it's still not quite accurate. In the late 90s, observations of supernova, measuring the redshifts of type 1a supernova, allowed it seemed to very strongly favor the idea that not only is the universe accelerating, but the universe is in fact, expanding, but it's expanding at an ever accelerating rate. And recall, I remarked earlier in discussing general cosmological models that an accelerated expansion will happen if there's a large lambda, a large cosmological constant that dominates over regular energy. So it's a more or less a straightforward conclusion from observation of accelerated expansion to the conclusion that there is in fact a non-zero cosmological constant, and it is moreover positive. And this now gives us today's standard model of cosmology, the so-called lambda dark matter model, also sometimes called the concordance model, which is what we will be primarily discussing for the rest of the week. So just to sum up, lambda CDM, standard cosmological model. Space-time geometry is taken to be flat, spatially expanding. Matter is radiation, so photons and neutrinos, ordinary matter, baryons and leptons, cold dark matter, and a cosmological constant. All of them idealized as perfect fluids. And the barotropic index of the cosmological constant is taken to be -1. And the geometry matter interaction is given by general relativity, the Einstein field equation with cosmological constant. Okay, didn't cover everything I wanted to cover today, but we'll pick up tomorrow and I'll see if I can cut some things out and actually get to some real philosophy. So thank you.
Well, thank you very much, Eric, for this wonderful panoramic about cosmological models and introductory conference about the problems that we will face in this week. We have 10 minutes for question because at 4:30 we have the coffee break. Someone has other question about this very Pascal? No. Eduardo, yeah, sorry.
I am not a physicist, so I have very Thanks. So I'm not a physicist, but so my question will be probably very naive, but I would like to understand better and piece the puzzle together, well, the pieces together of how exactly the lambda parameter, well, it's related to the Hubble parameter.
Mm-hmm.
Yeah,
So
I think I missed this part.
Mm-hmm. So lambda, there's no direct relation. I mean, it's not that they are physically identical or something, or that, but it is the case that if I know lambda theoretically, and I know the rest of the matter distribution, I can calculate the Hubble parameter. And it's also the case that if I observationally determine the Hubble parameter, and I have knowledge about the rest of the ordinary matter distribution, then I can infer the value of lambda. So they are mutually dependent on each other in that way. But and there actually is there is a rather straightforward formula one can write down that tells you, a rough and ready approximation for what the quantitative relationship is between lambda and the Hubble parameter. But actually, I'm not sure I actually wrote that down. I should have. If I did, if it wasn't on an earlier slide, I'll rectify that tomorrow.
Okay, thank you.